distance to center of slash point of mass distribution from axis of rotation, from axis of rotation, from axis of rotation, from axis of rotation, right? Look at here. To study on this, we'll be demonstrating this using a small experiment, a small practical scenario demonstration, right? That demonstration is called rotational chair, right? Rotational chair. Look at here. First, I'll explain rotational chair. Rotational chair, right? Look at here. Don't write anything. Just look at the board. Rotational chair means that's this kind of a round chair, made as it's rotatable. Now its seat is rotatable, right? And the experiment is something like this. A person can sit here. Look at here. A person can sit here like this on the chair, right? And we'll be basically considering two scenarios of this rotational chair. I'll show you a video of this as well. First, I'll explain and then I'll show you a video, right? And in this case, hands or arms are spread out, and in this case, arms are taken closer to the body, right? Now this is the impact. Let's consider these two scenarios as A and B. Let's consider these two scenarios as A and B. Look at the board. Right? Now, since there are no any external unbalanced torques or external unbalanced forces are here, what is conserved here? Angular momentum is conserved, right? Since there is no external unbalanced torque on the system, right? Angular momentum is conserved. Let me mark the rotational directions as well. Let's say rotational direction of this is this, and rotational direction of this one is also same. And only difference is whether the person has closed or taken the hands close to the body, or he has spread the hands away from the body. That's the only difference, right? So this is some learning from angular momentum that we covered the last day, right? Angular momentum is a conservation, no? It's conserved. Angular momentum is conserved, right? So therefore, see, now before coming to angular momentum, let me introduce these two cases. This is when hands are, don't write anything, just look at the board. When hands are close to body. When hands are close to body, and this scenario is when hands are fully stretched. Fully stretched means that is spread away from the body, right? In moment of inertia, distance to center of mass distribution means distance to center of mass distribution means that is basically changing with the mass distribution or the spreading of mass. And you have an idea about center of mass, no? Right? We covered under center of gravity, center of mass, right? Then higher the distribution of mass, higher the distance to mass distribution, right? Compact the distribution of mass. More compact means lower the distribution to center of mass, right? So having that idea in mind, look at here. Now, if hands are close to the body, compared to this scenario, mass distribution here is more compact, narrows. It's narrow. So therefore, let's consider these two are RA and RB. Therefore, RA is less than RB because mass distribution here is lower compared to this. Here hands are spread out, so distribution of that mass is higher, right? Very much similar to center of mass and center of gravity. Higher the mass distribution, higher R. So therefore R is higher, right? Now if R is higher, what happens to I? I becomes higher, right? Then with this, I can say therefore IA is also less than IB. Clear? But look at here, but I'll be writing here, but we know according to angular momentum, according to angular momentum, but according to angular momentum, I omega is a constant. I omega is a constant, right? According to angular momentum, I omega is a constant, right? When I increases, then omega should decrease in order to make this balance, right? So when I increases, then simultaneously omega decreases to make this a balance because K is a constant. K is a constant, right? Now, higher the I, lower the omega, which means the relationship between these two is something like this. This is the relationship between these two, right? So therefore, higher the I, lower omega. Therefore, higher I means lower omega. Here, omega A is greater than omega B, right? So I'll mention it here as well. I'll mention it here as well. Therefore, less I means higher omega. Omega A is greater than omega B, right? So this impact is called angular momentum, and this is how the mass distribution contributes in moment of inertia. When moment of inertia changes, according to angular momentum, omega also changes. So therefore, what happens here is when hands are closer, right? Look at here. While we are sitting on the rotational chair, right, or rotating chair. Now, if we close our hands like this, angular momentum increases. Sorry, angular velocity increases. You can clearly see that the angular velocity increases. And when hands are stretched, clearly the angular velocity decreases and we are rotating slowly. But when hands are close to the body, the speed, the angular velocity increases. Right? So that is how this impact is demonstrated. That is how this impact is demonstrated. Right? Using rotational jar. This is called the rotational jar. Right? Sometimes in some school laboratories, rotational jars are available. Right? Sometimes not. I'll be showing you a small video clip on rotational jar as well. Right? So first, take this down from here up to here. Take this down from the beginning. And if you have any questions, please raise. Please raise if you have any questions. Any other clarifications needed? Take down everything. Okay. Can everybody see the screen? Can everybody see the screen? Yes, right? Now I'm going to play this video. Watch this video very carefully. And this is the rotation shaft. And here, uh, two hammers are also kept on the hand to increase the mass distribution further. Fine? Okay. Uh, no need to turn on the volume. I have turned on the subtitles. You can read it out and just observe what happens here. Then I'll explain again. Right? Okay. I'll be playing this only once. So watch the video carefully. Right? Watch this video very carefully. Okay. Watch this video. That is called the rotational shaft. Observe the speed. Observe the speed. And once hands are closer, see the speed suddenly increases. Angular velocity suddenly increases. Right? I'll put this link to the chat as well if you need to watch it later. Right? I'll be putting it to the chat as well. See? Give me a second. I'll be putting it to the chat, the link of the video that I played. You can watch later if needed. So if needed, you can watch it there from that link, right? And for today's lesson, the other learning materials required will also be put to the chat box. Okay, I have sent the tube for today from circular motion to the chat box as well. For online students, you can download the soft copy from there, right? So you can see it in the chat box now, right? And if you have any more questions other than that, kindly let me know. Kindly let me know if you have any other questions other than that. Right. So that's about rotational shaft. Okay. So below that, first point, write down. First point, write down. when hands are stretched, 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 mass distribution increases. When hands are stretched, mass distribution increases. When hands are stretched, mass distribution increases. Right? Within brackets, mention this. I equals mr star. When this increases, I also increases. Mention this within brackets. When hands are stretched, mass distribution increases. Second point, according to angular momentum, according to angular momentum, second point, according to angular momentum, according to angular momentum, product of I omega, product of I omega, according to angular momentum, product of I omega, product of I omega is constant. Product of I omega is constant. For the same point, therefore, omega decreases when I increases. Therefore, omega decreases. Therefore, omega decreases. Omega decreases when I increases. Therefore, omega decreases when I increases. To keep it a constant. 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 Right? And mention this within brackets. I omega equals K, and when I increases, omega decreases, something like this. Because at the end of the day, K should be remains constant. I omega, product I omega is a K, that's a constant. So it should be remain constant. Right? Okay. Now let's see another application of this. Let's see another application of this. Write this down. Let's consider. Write down. Let's consider. Write down. Let's consider. Let's consider. A sphere and let's consider a sphere and a sphere and a ring of a sphere and a ring, a sphere and a ring of radius r, radius r, radius r, and mass simple m, and mass simple m. Released at rest from, released at rest, released at rest from, released at rest from, released at rest from, released at rest from top of top of two identical inclined planes. Release at rest from top of two identical inclined planes. Two identical inclined planes. Two identical inclined planes. Right? Determine who comes. Determine who comes. Determine who comes. Determine who comes to the bottom of the plane. Determine who comes to the bottom of the plane. Determine who comes to the bottom of the plane first. Determine who comes to the bottom of the plane first. Determine who comes to the bottom of the plane first. Right. Take this down. Take this down. And consider this scenario as A. Consider this scenario as A and this scenario as B. And I will give you a hint, then you can try. Listen, this is the hint. This is the hint. This is a ring, no? Ring means there is no mass inside. Ring is something like this. Mass distribution is only here. Mass distribution is only here. And this is a sphere. That's a solid sphere. So mass distribution is all around. Even though the distribution is different, I clearly gave you that these two masses are same as M. Masses are same. Right? Okay. Then what I ask is, like, who comes first now? Besides that, we need to know about angular velocities. Higher the angular velocity means less time consumed. So they comes first, right? Therefore, this is the hint. You can start arguing from mass distribution, and then you can connect it with moment of inertia, and then connect moment of inertia with omega using angular momentum. Same steps that I considered in rotational chair, and then get the relationship between omega values of these two. Right? Higher the omega, lesser time taken to come down, which means they comes first. Higher omega means higher angular velocity, higher speed, they comes first. Right? Okay, copy down and try it. I'll give you 2-3 minutes. And online students, if you got the answers, you can put whether it's A or B, who comes down first. And for you also, that same the answers. Okay. B. Let's see. See, now answers are incoming, so you can try it out quickly. You can try it out quickly. You can send your answers. You can send your answers. Doesn't matter whether you are a new student or an old student. You can try this out. Without having any prior knowledge, if you listen to the things that I explained from the beginning today about moment of inertia, this can be tried out. This can be tried. A comes first. Let's see, let's see. You said B. Okay. It can only be either A or B because there is nothing given as C, no? So it's either A or B. Let's see. Again, I'm getting like a mix of answers. And mass distribution is very comparative to center of mass. Very comparative to center of mass. Not center of gravity, center of mass. Center of mass. What do you say? B comes first. B, B. You are still at B. Now A. A. Anyone who says both comes down at the same time? Anyone says both comes to the bottom at the same time? Anyone with different opinion? On? See, let's see. Look at here. Time is enough. Look at here. Okay. Here in this ring, mass is distributed. Look at the board. Look at the board. This is how we should argue on this to get this type of a question. Right? See, mass is distributed only from here to here now, in this strip. Right? So therefore, center of mass distribution is somewhere in the middle of this. Somewhere in the middle. Center of mass distribution. Because mass is distributed from here to here. Mass is distributed from here to here. So center of mass distribution is in the middle of that mass distribution. Right? Very comparative to center of mass. Here, mass distribution is from center up to here. Therefore, center of mass distribution is around the middle point of that distribution. Is that clear? Right? Now, what about the lengths? If I consider them as RA and RB, they are not radius. They are not radius. They are the distance to mass distribution. Right? Here, the mass distribution is somewhat closer compared to this. This is closer compared to this. So, therefore, RA greater than RB. Right? When you are checking mass distribution, check where the actual substance or actual mass is distributed. Right? Since there is uniform, center of mass distribution is at the center of that distributed part. At the center of that distributed part. Very simple as that. RA greater than RB. Right? Then according to this, I mentioned the equations here. Since I equals MR squared, higher R means higher I. So therefore, IA is greater than IB. IA is greater than IB. Right? Again, I mentioned the equations here. But since I omega is constant, I and omega are always inverse. I and omega are always inverse. Right? I and omega inverse. Then higher I means lower omega. Higher I means lower omega. Now, omega B greater than omega A. Omega B greater than omega A. Higher velocity means it comes first. Therefore, final answer is B comes first. B comes first. B comes first. This is the argument. This is an easy argument using moment of inertia. Moment of inertia and angular momentum. Right? This is another MCQ type questions that you are getting in the exam. This is an MCQ type question you are getting in the exam. To compare moment of inertia. To compare moment of inertia. Right? I hope it's clear. You can ask anything if you have. You said B. B, then A. You can ask anything if you have any questions. You can ask anything. So can you please explain the center of mass distribution again? Simply, center of mass distribution is where uh, the center of, or the exact center, or the middle of the exact mass distribution part. Now, if I use another object, see, let's consider this object. Look at here. Let's consider this object, right? Mass is distributed from here to here. Mass is distributed from here to here. Then center of mass distribution is at the middle of this part, right? At the middle of this part, right? Simple as that, right? That is the middle point or center point of actual mass distribution, right? Center point of actual mass distribution. Here, the mass distribution is from center to the circumference. Then around the middle. Actually, that is in RO2. That is in RO2. But here, mass is distributed only from here to here. Then that should be in middle of that strip. In the middle of that strip. Right? That is how it's argued. A, right? And online students, please download the route from the chat box and get ready because we are about to start circular motion, right? Download the route from the chat box and get ready. You can download the route and get ready yourselves. Prepare yourselves. I have put the route to the chat box. Yes, sir, clear. Right, okay. Done. Okay. So then that's it, and that's all for rotational motion and moment of inertia. So we have successfully concluded the rotational motion with this. This is the completion of the successful completion of rotational motion from the sketch to here with all applications and everything. Right? Okay. Now we are going to move on to the today's lesson. See, we are going to move on to the today's lesson. To at the board. So as a next heading, write down circular motion. As a next heading, write down circular motion. Circular motion. Circular motion. Right. So before circular motion, what are the other types of motions you know by now? What are the other types of motions you know by now? Linear motion. That was the first motion we learned. Linear motion. What else? Projectile motion. I downloaded, but it is not visible. Can you send it again? Not visible. Can't you open the PDF? Can't you open the PDF file? Same problem. Ah, is that? it be open for everyone? Is that the same? Give me a minute. Is that the same? Same. Hmm. I'll send again. Can it's visible? Ah, it's only for some. What's the reason? Can be downloaded, right? Amra, can you download it and open it? Can you view the PDF? Yes, can view. Uh, so, is there anything wrong with your device? Or are you getting any error when you are trying to open the file? I couldn't download. Why? Hmm. Let me send again and let's check again whether it's working. If not, I'll see another option. And I don't think it's not working because now it's working in my devices, and for some students also it's working. Let's try again. Let's try again. Give me 2 minutes. Give me 2 minutes. So I'm going to put it to the chat again. Let's try again for one last time. And if it's not working, I'll see another option. Try this for the last time. And there was no any like apparent reason that you have not to be able to download it. Wait. Give me 2 minutes. Okay, can you check again? I have resent it to the chat box again. Can you check again? The students who couldn't download or if you couldn't open it, check again with the new file. Can you check again with the new file? And quickly confirm me whether it's working or not. Now okay. Others? I got like I think I got 4 5 uh, messages from students saying it cannot now working. Okay, right. Okay. Oh, okay, right, right. Okay, now okay, right? All right then. Okay. Now okay, right, right. Okay, good. So what I was asking was the other types of motions we know by far, right? Linear motion, projectile motion, rotational motion. We just completed, and here we are in the fourth type of motion. You are going to learn, right? The fourth type of motion you are going to learn, that is circular motion. And altogether we have six types of motions. Altogether we have six types of motions in our syllabus. And other two types coming up are simple harmonic motion and helix motion. Helix, or we call it spiral motion. Those are the other two motions coming up. Now we are going to start the fourth type of motion today, right? And each and every type of motions are they are having similarities as well as differences, and they are very comparative, and they have their unique features, right? And when it comes to motions like rotational motion and circular motion, even they have their own similarities and differences, right? Two different motions, actually two completely different motions, right? Okay. Any idea about what a circular motion is? Now I explained what the rotational motion is in rotational motion. What was the rotational motion? So before the circular motion, tell me what was the rotational motion? Because most of the students are messing up with the rotational motion and circular motion, and some students are there who think like both are same. Both are not the same. They are completely two different motions. Completely two different motions. Look at here. The part we just completed was rotational. Rotational motion. And today we are going to start circular motion. Now we are starting circular motion. Right? So there are some students who think these two are same, not the same. Tell me, what's the rotational motion? What is the rotational motion? That's a keyword. If an object travels around its own axis, that's a rotational motion, right? The keyword comes here is if an object travels around its own axis. If an object travels around its own axis, that is a rotational motion. Now, as an example, consider this as an object, this pen as the object, and if this travels like this about its own axis like this, that is a rotational motion, right? The same object, if it travels around an external axis, say this is an external axis somewhere here, and if this travels around that external axis, if it travels around that external axis, automatically this becomes a circular path. Automatically this becomes a circular path, and that is called a circular motion. And that is called a circular motion, right? So in circular motion, first thing is there is an external axis always, right? For the object, there is an external axis, and and the path is circular. Path is circular. Circular motion, right? As the name suggests, the path is a circular path. Sometimes it can be a complete circle, or sometimes it can be a partial circle, a part of a circle. Still, that's a circular motion, right? Clear enough? Clear enough? Right. Okay. Under circular motion, write down. Under circular motion, write down. If an object travels, if an object travels, if an object travels, if an object travels if an object travels around an external axis, around an around an external axis. If an object travels around an external axis, if an object travels around an external axis slash external point, external axis slash external point, external axis slash external point in a circular path, in a circular path, in a circular path in a circular path, it's called a circular motion. 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 Right? Underline or highlight external axis, external point, and circular path. External axis, external point, and circular path. Those are the keywords. Those are the keywords. Those are the keywords. Okay. For both rotational motion and circular motion, the object only has an angular velocity, omega. Right? The object only has an angular velocity. Therefore, all the equations we learned in rotational motion about angular velocity are valid here as well. Right? All the equations we learned in angular velocity, in rotational motion about angular velocity are valid here as well. Right? There are 5 equations for angular velocity. Right? Let's recall these equations. Tell me the 5 equations of omega. Tell me the 5 equations of omega. 5 equations of omega. Two phi f. I'll write it somewhere here. What's the general equation of omega? Theta over t. Yeah. General equation is theta over t. General or basic equation is theta over t. Then P over 2 phi f, 2 phi over capital T. Then last one, 2 phi RPM over 60. 2 phi RPM over 60. So these are the 5 equations of omega. These are the 5 equations of omega, and these 5 are valid here as well, because for a circular motion also the object has an omega, not a linear velocity, because that will be a circular path, no? Circular path, angular velocities. Circular path means angular velocities, right? And considering these two, we can say f is 1 over t. Considering these two, we can say f is 1 over t, right? I'll quickly explain the meanings of these terms as well, since there are new terms. Here, I'll quickly explain the meanings of these words, because these are terms, because for the applications, we'll be using these equations, we'll be picking these equations with the given data, right? And the requirement. Yeah, tell me theta. Angular displacement, T, time, V, tangential velocity, R, radius, F, frequency, periodic time or period, RPM, revolutions per minute, or we call rotations per minute. Both are correct. Revolutions per minute or rotations per minute. Right? Those are the meanings. Right. As a small subheading, write down equations of omega, or equations of angular velocity within brackets omega. Subheading equations of angular velocity. Equations of angular velocity within brackets omega. Equations of angular velocity within brackets omega. Mention all 5 equations. Mention all 5 equations. Mention all 5 equations. Right. That right. Okay. Now look at here again. Now let's consider this pen again. Let's consider this pen as an object. Right. Now, if this pen undergoes this kind of a motion, see this type of a motion, right? It's a circular path. Look at here. Look at here. Don't do anything. Just stop all your work and look at here. Right? Stop all your work and look at here. If this object undergoes in a circular path like this, right? Now the point of rotation is an external point, right? And this path is circular. Path is circular. So therefore there is a circular motion. And if the same object undergoes something like this, is it around an external axis? Is it around an external axis? Yes. Is it a circular path? Yes. So that is also a circular motion. So therefore, when it comes to circular motions, that circular path can be at any direction or along any direction, right? Can be either horizontal or vertical or inclined or anything, as long as the path is circular. That's a circular motion, right? Listen very carefully. But for A levels, we only have two circular motions. They are horizontal circular motion and vertical circular motion. In between, inclined circular motions are not here in A levels, right? Even for A level maths, that is not here, right? But if you are going towards higher math sides, higher physics directions, then you will get to know about the inclined circular motions as well, right? So therefore, in A level physics, and if you are a combined math students in A level maths also, we will be only sticking to vertical and horizontal circular motions. But it doesn't mean only these two exist. No, right? For any direction, that's a circular motion. But for our syllabus, since we only have vertical and horizontal circular motions, we'll be stick to those two. Actually, the reason is when it comes to inclined circular motions, in terms of the motion, that is very advanced and complex. So that is why that is not here for A levels. Right? Okay. Now look at the board again. See, look at the board again. Now I'm going to consider an example object which is undergoing in a circular motion, right? Which undergoes in a circular motion. Look at here. Don't write anything. Don't do anything. Just look at here. Okay. This is a circular path. Right? And let's assume an object starts a circular motion here. This is the object. Look at here. Let's assume this object starts a circular motion here, right? And let's say that is t equals 0 of the object. That is where the time starts, measuring time starts, right? And now starting from here, look at the board. Starting from here, this object or this particle travels from here to here to here to like this along this circle, and it completes a circle once it is back at the original point again. So it completes the entire circle, right? So when it travels from here to here like this, that's a circular motion. When it travels from here to here like this, that's a circular motion. And if it is back at the starting point, back at the original point, if it is back at the original point, it has completed exactly one circle, right? Exactly one circle. Periodic time is, what is periodic time? Periodic time is the time taken to complete a circle. Yeah, one rotation or one circle. Periodic time in rotational motion is the time taken to complete a single rotation or single circle. So therefore, if it is that at this point again, which means it has spent one periodic time, one period. It has spent one periodic time, one period. Right? So therefore, now if it undergoes the circular motion like this, right? Once it is that at this point again, T equals capital T. T equals capital T because it has completed one circle, which means it has spent one periodic time. Right? Now, if I consider some example points of the objects when it is undergoing the motion, right? These are some random points. At some point it will be here. At some point it will be here. Will be here. Will be here. 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 And here. So likewise, it undergoes. And actually there are infinite number of points from here to here, right? But for our ease of demonstration, I use some random points here and there, right? Random points here and there. And now let's assume angular velocity of this object as omega, and that has a uniform value. Let's assume angular velocity of this object as omega, right? In the circular motion also, now it has an angular velocity. No? If an object is having an angular velocity, definitely it has a tangential velocity as well, because omega equals v over r, right? Look at here, see these logics. Since omega equals v over r, if an object has omega, definitely it has v. V is not a velocity, that's a tangential velocity. V is not the velocity, that's a tangential velocity. Therefore, which means this object also has tangential velocities. This object also has tangential velocities. Now I am going to mark tangential velocities at each of these points. I am going to mark tangential velocities at each of these points. Look at the board. Look at the board. Always starting from here onwards. Tangential means that is along the tangent like this. Let's say V, right? This is also along the tangent like this. Let's say V, right? Along the tangent V, along the tangent V, along the tangent V. This is also along the tangent V. This is also along the tangent V, along the tangent V. So likewise, it has tangential velocities. Tangential velocities, and its direction changes second to second, time to time. Direction changes. So therefore, it's not a uniform velocity. Tangential velocity is only for a point. We can't say it's a uniform velocity because direction changes. There's a velocity, direction should remain same, no? Right? We can say it's a uniform speed, but we can't say it's a uniform velocity, right? And from the equation, we can say V equals R omega. See? From this equation, V equals R omega. V equals R omega. So therefore, this V equals R omega actually. So I will mention R omega also in some places. This V equals R omega. This V equals R omega. Right? And now if it takes, listen carefully, if it takes, these are the introduction parts. Now if you get the introduction properly, circular motion is nothing. Now in physics, in most of the lessons, not most actually, in almost all of the lessons, that's there. We have few concepts, and that opens up to any number of questions, any number of applications. So therefore, once you grab the basic theories, basic concepts here in any kind of a lesson, right? Tackling questions is very easy, right? The difficult part here is or the part that you should be very mindful is grabbing these concepts. Concept is the new thing. Having the concept is everything. So listen carefully. Listen carefully. Now, if it takes a time t, capital T, to complete the entire circle, to complete an exact one fourth of the circle, it takes one fourth of time now. Therefore, I can say this is when t equals t over 4. This is when t equals t over 4. Right? No problem. No? And this is half of a circle. So I can say this is when t equals t over 2. Correct? No? And this is three-fourth of the circle, three-fourth, three quarters, three-fourth of the circle. So I can say this is when t equals 3t over 4. And this is when t equals t. Right? That is when t equals t. And now, let me mark omega in other places as well. Now, even though, look at here, even though this omega remains same, even though this omega remains same, this omega is constant. Even though this omega remains same, direction of tangential velocity changes time to time. But direction of omega doesn't change. Direction of omega doesn't change. Omega is a uniform angular velocity. This uniform angular velocity, but v changes. So therefore, there is a uniform speed, not a uniform tangential velocity. We can say it's tangential velocity for a given point only. Can't say it for a range. If a range is considered, direction changes. That's the case. Understood? Now, these are the fundamentals or the foundation basic concepts about the circular motion. Right? So first we will see all basic concepts and we are going to start applications. Right? We are going to start applications. Right? Is that clear about the motion I explained here? Take this down. Take this down quickly. Take this down. Or let's write this way. We didn't write anything at the top, right? Write down. Let's consider. Let's consider. Write down. Let's consider. Let's consider. An object travels. Let's consider. An object travels. Let's consider an object travels. Let's consider an object travels in circular motion. In circular motion with uniform angular velocity omega. 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 Right? Now take this down. How to register? You need to register. I'll drop other details with the flyer to the chat box as well. From there, you can see the registration links and the other hotline numbers and all those things. Contacting them, contacting those numbers, you can get the registration done. Otherwise, you can navigate yourselves to lms.mathlab.lk. I'll be forwarding the flyer, and in that flyer, all details are there, and you can register yourself by your own. Yeah, I'll forward it. We'll forward it. So copy it down. Copy it down. You can see all details from that flyer I just sent to the chat box. Right, you can get all details. You can see all details there, and group links are also there. For updates, you can join to the groups, and for the registration, in the flyer itself, the website and the hotline numbers are mentioned, so you can do it using any of these means. Finish. Right. Now, below this, take this note down in point form. Take this down in point form. First point, velocity of a circular motion. First point, velocity of a circular motion. Velocity of a circular motion. Velocity of a circular motion acts towards tangential direction. Acts towards tangential direction. Acts towards tangential direction. Everybody knows what tangential means, right? Right. In rotational motion, we have discussed. Is there anyone who haven't heard the word tangential? Tangential means along the tangent. And if the tangential direction and center is connected, it will be a right angle. It will be a right angle. Right? Second point. But velocities of above points are not equal. But velocities of above points are not equal. What is the reason? I explained before. What is the reason to say that velocities are not equal? What is the reason? What is the exact reason? The exact reason to say that velocities are not constant. Velocities are not equal. I explain. Direction, direction is not the same. About the direction. Now, to check on a vector, we are interested about only two things: magnitude and direction. Now, magnitude of the velocity remains same. See, v, all around, and that's our omega. Magnitude remains same, but direction changes from point to point. So velocity is not equal. Right? Velocity is not equal. right, within brackets, to the same point within brackets, direction changes from point to point, 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 even though magnitude remains same, even though magnitude remains same. Direction changes from point to point even though magnitude remains same. And another small message for all of you. In a coming week, in one of the coming weeks, I'll be conducting another open seminar on plotting graphs. Right? Something like this. Some students might know this and some might not know this. From our 50 MCQs in the MCQ paper, out of 50 MCQs, you will be getting 10 graphs. Right? You will be getting 10 graphs out of 50. Right? Listen to this. From 50 MCQs, you will be getting 10 graphs in our A-level physics paper. You are getting 10 graphs in our A-level physics paper. 10 graphs means 10 questions. 10 questions means 10 marks. 10 marks means that's a very significant, very considerable amount of marks. 10 marks. That's 10% from all, from 100. Right? It's a life-changing mark, no? 10%. 10 marks. Not even 10. Even a single mark is life-changing. Right? So therefore, there are different special techniques when plotting graphs. Otherwise, graphs are not a thing we can like parrot and do. Right? When axes are given, we should be able to draw the graph. We should be able to plot the graph. Right? That's the purpose of graphing. Right? Otherwise, now this is something like this. Now let's say you know the variation of Boyle's law. Variation of Boyle's law. You know the variation of PV as this. Let's say you know this. You all know Boyle's law, no? Right? Now, if the same graph comes as let's say 1 over P with 3 or something, sometimes you will get confused. But this is also from Boyle's law. This is only the standard graph. This is only the standard curve. But when these axes are changed, then the graph changes, the shape changes. Right? Likewise, we have to adjust ourselves to the question and plot the graph. Therefore, for A-level physics, there are different techniques to be used when graphing. Right? There are different techniques to be used when graphing. Right? Therefore, I'll be conducting another open session on graphing, only on graphing, to give you all this knowledge, to transfer all this knowledge on graphing. Right? And this is the gravity of graphing in the MCQ paper. And other than this, these graphs are coming in all types of papers like structured essays and essays as well. Right? Definitely 10 MCQs are there. Therefore, we have to know how to plot graphs. There are techniques. There are techniques by identifying independent and dependent variables. There are techniques to plot graphs. Whether it's y equals mx or mx squared or y equals 1 over x or 1 over x squared or m root x or likewise. Different shapes are there. Right? Maybe trigonometric graphs. Different cases are there. So therefore, I'll be conducting the open session on graphing, only on graph plotting. That will be only on graph plotting. And the focus is you, but any 25, 26 or 27, even 27, I don't mind. Any student can participate. But the main focus is you and 25. Right? The only batch I have here in Dehivala is the 26 batch, no? Right? So therefore, basically I'm going to focus on this 26 batch. And I will convey the message to the 27 students as well. And for 25 students also, I'll be conveying the message because they are also 6 months short of the exam and ahead of the exam. And that's a critical time to get to know about graphing. So therefore, I'll be conducting it as an open session for all of you on graphing. right? And this is the gravity. You can secure 10 marks. You can secure 10 marks if you know the methods, the techniques, the tools that we use to plot graphs, right? So therefore, keep that in mind. We'll be doing this session in one of the upcoming weeks, maybe during the same month, most probably during the same month, May. Most probably that will be during the same month, May, right? Yeah, that will be conducting as both online and physical. If you are coming physically also, that doesn't matter, and you can join online as well. I'll be conducting it as a hybrid session. And the reason to pass the message to you is, now if you have any contacts of any students of any batch, right, they can participate to this, right? No any prior knowledge is required, right? This is all about graphing, right? All about graphing. No any prior knowledge required, and this is the ultimate target, because once you get to know about graphs, you can secure these 10 marks, right? I'll share my flyers once the session is scheduled. Keep that in mind, and pass the message to your colleagues, right? From 25 onwards, right? Theory, revision, anything, that doesn't matter. So I'll be conducting this as a support for all of you, because graphing is not something we have to like teach separately. That is not something like that, right? But I'll be doing that as support for all of you to secure these 10 marks, right? So even though the graphing is not taught separately, you are getting 10 graph questions. Therefore, it is something to be taught, right? So that's why I'm going to do this session, right? Something to secure these 10 marks. 10 means that's a huge amount, because even from a complete essay question, you are getting only 7.5 marks. From a complete essay, you are getting 7.5. And for 10 graphs, you are getting 10 graphs, 10 marks for 10 graphs. That's a huge amount, right? So that's why, as a support, I'm going to conduct the session, right? Okay. I'll update you on the other details soon, and you can join the WhatsApp group and be there for the other WhatsApp group or channel. That doesn't matter. I'll be sharing the updates on both. Right. What was the last point I mentioned? Direction changes from point to point even though the magnitude remains same. Right. Next point. Therefore, objects cannot travel. Therefore, objects cannot travel in circular motion. Therefore, objects cannot travel in circular motion with uniform velocities. Therefore, objects cannot travel in circular motion with uniform velocities. Next point, objects can travel in circular motion. Objects can travel in circular motion either with uniform angular velocity, or with uniform speed only. Either with uniform angular velocity or with uniform speed only. Either with uniform angular velocity or with uniform speed only, right? And underline uniform angular velocity, underline now, highlight uniform angular velocity and uniform speed. Right? Next heading. Next heading. Acceleration components. Next heading. Acceleration components in a circular motion. Acceleration components in a circular motion. Acceleration components. Acceleration components in a circular motion. Acceleration components in a circular motion. Acceleration components in a circular motion. Okay, below that write down. Let's consider an object travels with, let's consider an object travels with, let's consider an object travels with, let's consider an object travels with an instant angular velocity. Let's consider an object travels with an instant angular velocity. With an instant angular velocity omega at a point. With instant angular velocity omega at a point. Look at here. Now again, I am going to consider another object which undergoes in a circular motion, right? Which undergoes in a circular motion. So let's consider the object is here, right? Let's consider the object as here, right? Look at the board. Look at here, and the radius of circle is r, right? And speed, angular velocity here as omega, right? Okay. When comes to a circular motion, listen carefully. Here, there's the first difference with the rotational motion of a circular motion. There's a similarity and a difference as well, right? Now, if there's an angular velocity, if omega is acting here as angular velocity, definitely there should be angular accelerations, right? Definitely there should be angular accelerations. If omega is not a constant, there should be an acceleration, and that is angular. That we call as alpha. What is the relationship between omega and alpha? What is the relationship between omega and alpha? Omega is, or alpha is delta omega over t. Alpha is delta omega over t. Right? Now linear acceleration is, it is not visible. Will be mentioned here, somewhere here. Alpha is actually delta omega over t. If we think of linear motion, right? Linear acceleration is delta v over t. Linear acceleration is delta v over t. Similarly, angular acceleration is delta omega over t. Right? That we started our discussion way back in rotational motion in equation conversions and parameter conversions. Right? So therefore, alpha should be there. If omega is not constant, then alpha is there. Right? And when that omega changes, this v also changes. No? When that omega changes, v changes. V is tangential. Right? So therefore, that respective acceleration changes. And that acceleration component is called the tangential acceleration component in a in a circular motion. Right? That acceleration component is called the tangential acceleration component in a circular motion. Right? And that will be along the tangent. Look at here. That will be along the tangent like this. there is an acceleration, there is an acceleration along the tangent. So we denote it by AT. We denote it by AT, tangential acceleration. We denote it by AT, tangential acceleration. Right? And there is another acceleration component in a circular motion. There is another acceleration component in a circular motion, and that acceleration component always acts towards the center. That acceleration component always acts towards the center, right? That is always towards the center, and this component is towards the center, and that component is called centripetal acceleration. Centripetal acceleration, and denoted by AC. Centripetal acceleration, that is towards center, and these two accelerations are perpendicular to each other at any point, because this is acting towards the center, this is tangential. Towards the center direction and tangential direction is always perpendicular in a circle, no? So therefore, it's perpendicular to each other, right? There are equations for these two separately, right? Equations are like this. Don't write anything, just look at the board. These are the most important basics about the circular motion. Alpha is very much comparative with and very much similar to the alpha we have in rotational motion, right? So therefore, tangential acceleration can be written as AT, can be written as R alpha. Tangential acceleration can be written as R alpha. A equals R alpha in rotational motion. A equals R alpha. And for AC, there is a different acceleration, and it can be written as, there are two ways actually, V squared over R or R omega squared. V squared over R or R omega squared if velocity at this point is V. If velocity at this point is V. Right? So this is how these two acceleration components are different from one another. Right? Right? Clear? Right. And explain it again. Simply, since there are velocities along the tangent, when the velocity changes, along the tangent acceleration changes. Therefore, tangential acceleration is there. If we have a tangential velocity, there should be a tangential acceleration. No? So this is tangential acceleration, and it comes from AT equals R alpha, very much comparative with the rotational motion. A equals R alpha. So here specifically that is AT, so AT equals R alpha, right? And this is called the centripetal acceleration component. Centripetal, and that is acting towards the center only. That is acting towards the center only. Reason for this acceleration is a force which called centripetal force, and we are going to discuss about that force in the coming part. That is how this acceleration generates with centripetal forces, right? With centripetal forces, right? And it can be written as these two. Just know about these equations here and about the centripetal force and the generation or the exertion of this acceleration we'll be discussing in coming parts. Right? Any other questions? Any other questions? Online students? Online students? All good? All clear up here? Clear. Right. So we are going to take this down. Right. We are going to take this down. First, take down this diagram. Take down the diagram. Take down the diagram. So how was your May Day? May Day, public holiday. No school, no rush, roads are empty. Right? Roads are empty compared to other days. For you?
Usually, right?
Yeah. Copy down the diagram. Copy down the diagram. Only the diagram. Only the diagram. Don't write anything. Copy down the diagram with these acceleration components. That's it. Finish. Okay. Uh, Below this, write down. There are two acceleration components. There are two acceleration components. Write down. There are two acceleration components. There are two acceleration components. There are two acceleration components acting. There are two acceleration components acting on an object. Acting on an object. Acting on an object which undergoes. Acting on an object which undergoes circular motion. Which undergoes circular motion. Right? Row number one. Put row number one. Put row number one and write down tangential acceleration. Write down tangential acceleration. Tangential acceleration. Tangential acceleration. Tangential acceleration. Tangential acceleration within brackets 80. Within brackets 80. Within brackets 80. Right? And below mention this equation and highlight this. Only this equation, only this, and highlight the equation. 80 equals R alpha. Mention the equation, first equation, this one, first one only, and highlight it. First one only, and highlight it. Introduce terms, R, radius of circle. Introduce terms, R, radius of circle. R, radius of circle. R, radius of circle. And alpha, angular acceleration. Alpha, angular acceleration. Alpha, angular acceleration. Right? That is very much same as alpha in rotational motion, angular acceleration. Right? Then row number two, centripetal acceleration. Row number two, like this. Centripetal acceleration. TRI, centripetal acceleration. Centripetal acceleration. Centripetal acceleration. Centripetal acceleration. Right? Within brackets AC. Within brackets AC. AC. Right? Now write down only this equation. Write down only this equation. This one. This one. And highlight this. This one and highlight. Write down this one and highlight. And if any one of you needs the derivation here, see, something additional, look at here. If the derivation is needed, v squared over r, no? V squared over r. But we know v equals r omega. V equals r omega. Then v squared can be written as r omega whole thing squared, no? No problem. V is r omega, right? Derivation. Then this is r squared omega squared over r. 1 r to r cancels. R omega squared comes. So that is why v squared over r equals r omega squared. That is how v squared over r equals r omega squared. Right? So if anyone didn't notice this derivation, you can have a note on this. Right? So I didn't explain because you can notice it easily because v equals r omega. V equals r omega. If you didn't notice, this is how I got it. This is how I got it. Right? Introduced terms here of this equation. Introduced terms. V. What is V? Tangential velocity. V tangential velocity. V tangential velocity. Then R radius of circle. R radius of circle. R radius of circle. Omega angular velocity. Omega angular velocity. Okay. Look at here again. Look at here again. Now, if there are two acceleration components for a circular motion, then where should be the actual acceleration? Where should be the actual acceleration? Is it AC or AT or both? Now, what's the net acceleration or actual acceleration or let's say resultant acceleration? Where is it? It should be in between because these two are two acceleration components, two vectors. So therefore, the actual or the resultant acceleration component acts in between. Right? Okay. Again write down. The actual acceleration component within brackets resultant acceleration. The actual acceleration component within brackets resultant acceleration. The actual acceleration component within brackets resultant acceleration acts in between resultant acceleration acts in between what? AC and AD. Acts in between AC and AD. Right? So therefore it's something like this. Look at here. Now these two components are like this. AC and AT. Right? So the actual acceleration component of the circular motion is in between like this. Right? And this actual acceleration component can be written as root AC squared plus AT squared because two perpendicular vectors. They are two perpendicular vectors, right? And if the direction is needed, direction can also be written as tan theta, right? So let's say we need the direction with this tan alpha. So direction is tan alpha equals AT over AC. And these things are coming from vectors. These things are coming from vectors. Right? Okay. Now below that, starting from here, mention this part. Mention this part. Right? Right? Okay. Now listen again. Listen carefully. Listen carefully. These are the things you have to uh, implant in your heads because this is the foundation of circular motion. If these things are there, to be honest, frankly speaking, these applications are nothing. Applications are nothing, right? Now, first, you have to implant everything here inside your head now about the circular motion, right? Now, another question. Listen carefully. Listen carefully, right? Listen to the question. Now, if the object travels with a uniform velocity, right? If the object travels with a uniform velocity, right? Tell me which acceleration component is going to be zero, right? I'm asking whether it's AT or AC or both or none. Four answers. AC, AD, both will be zero. None of them will be zero. Four answers. Right? Repeating the question again. Listen, repeating the question again. If this object travels in the circular motion with a uniform angular velocity, uniform omega, uniform angular velocity, which acceleration component becomes zero? That's the question. Which acceleration component becomes zero? Think and tell me. Both. Reasons? What are the reasons? Tell me the reason. What's the logic? No idea? You? Online? AC. What's the logic? There should be a logic. Now, you should be able to justify your answer. Right? What's the argument? Any thoughts? No? AT. What's the logic, rational behind it? Any thoughts? Any thoughts? With a rational, with a logic? Online students, some says AC, some says AT. Okay. Justify it with the rational. Justify it with the rational. Now, if you have listened to the discussion, if you have listened to the discussion from the beginning, now by this time, now you will be clear on that. Now, that's why I'm asking this question. That's why I'm actually asking the question. Yeah, tell me, what's the rationale? Why you say AC is 0 and why some of you say AT is 0? AC is 0. Okay, what's the reason? Now, you can check with the equations. Now, equations of AT and AC are here, right? Equations of AT and AC are here. Then now you are maths students. No, maths means you are physics students. Physics means you are always having some mathematical approach. You should always have a mathematical approach, right? So therefore, by using the support of equations and other logics, justify your answers. That's it. Online students, others, I have got only 3-4 answers. There are 80 students online. Yeah, others. Tell me, what do you think? No idea yet? No? Both will be 0. Both will be 0. Then if both, then justify your answer. That's the only thing what I asked. If you say both are 0, justify it. If you say both are non-zero, then justify it. Right? If you say only one is 0, then you can justify why that becomes 0. Quickly. AT, because when V is constant, A is okay. No, any other idea? No. Look at here. Now you should be able to argue on this. Now what I said was, if omega is constant, no. If omega is constant, look at here. Now what I said was, if omega is constant. If omega is constant. What I said was, if omega is constant. Right? If omega is constant. If omega is constant, what can we say about alpha? If omega is constant, what about alpha? Oh, before that, if omega is constant, what about delta omega? If omega is constant, what about delta omega? If omega is constant, what about delta omega? What is the expansion of delta omega? Expand delta omega. Omega 2 minus omega 1. Omega 2 minus omega 1. That is final angular velocity minus initial angular velocity. Then if omega is constant, what about delta omega? 0. 0. 0. Yeah, 0. Right? If omega is constant, delta omega is 0. No change. No change. 0. If delta omega is 0, what about alpha? 0. If alpha is 0, what about 80? 0. 0. Simple as that. Simple as that. So 80 becomes 0. 80 becomes 0. Now check about AC. Omega is constant. Omega is constant. Omega is constant. This equation is R omega square. R is non-zero. Omega is constant. It doesn't mean omega is 0. Omega is there. So R omega squared is non-zero. Right? If omega is there, V is also there. R is also there. Non-zero. So therefore, AC is non-zero. Right? AC is non-zero. AC never becomes 0. Right? AC becomes if the circular motion stops only. If the circular motion stops, there is no circular motion there. Then only AC becomes 0. Otherwise, If there's a velocity, if there's an angular velocity, there is AC only. Right? Only AT becomes 0. Only AT becomes 0. I didn't get the correct answer from anyone. Right? Only AT becomes 0. Right? If the motion is uniform, if the angular velocity of the motion is uniform, only AT becomes 0, but AC never becomes 0. AC never becomes 0. Right? If stops. Stops means there is no circular motion at all. Right? If it stops, that's true. If it stops, only AC becomes 0. Right? If it stops, we don't call it a circular motion. If it stops, that's not a circular motion. Right? So that's why I say it never becomes 0 in a circular motion. Right? Understood? Okay, next point. Next point. These are the key things, key facts you need to know. Next point. When an object travels with, write down, when an object travels with uniform angular velocity, when an object travels with uniform angular velocity, when an object travels with uniform angular velocity, angular acceleration becomes 0. 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 Mention these equations. I will mention here. Got the board. Mention these equations. Alpha equals delta omega over t. Since delta omega is 0, alpha becomes 0. Right? AT equals R alpha. Therefore, AT becomes 0. Mention everything. So this is the logic. This was the logic I was seeking for. None of you gave the logic. This was the logic I was seeking for as physics students. Right? Then below that again, therefore, AT becomes 0. Therefore, AT becomes 0. Therefore, AT becomes 0. Therefore, AT becomes 0 when an object. Therefore, AT becomes 0 when an object travels. An object travels with uniform angular velocity. When an object travels with uniform angular velocity. Right? Next point. Next point. Centripetal acceleration. Centripetal acceleration. Centripetal acceleration. Centripetal acceleration is never going to be 0. Centripetal acceleration is never going to be 0. Centripetal acceleration is never going to be 0 depending on never going to be 0 depending on the behavior of the motion. Depending on the behavior of the motion is never going to be 0 depending on the behavior of the motion. Within brackets, accelerating comma, decelerating, accelerating, decelerating, accelerating, decelerating, or uniform velocities. Accelerating, decelerating, or uniform velocities. Right? Accelerating, decelerating, or uniform velocities. Okay. Any questions up to this point? Now we are 80% done about theory. Theory is in circular motion. We are 80% covered. 80% done about the theories in circular motion. Right? So any questions up to here? Never going to be zero. Stops, yes, but it stops. We don't call it a circular motion. So it's never going to be zero in a circular motion. If it stops, that is not a circular motion. Any other questions up to this point? Any other questions up to this point? All good? Online students? Online students? Okay, so we are moving on. Write down next heading, force components in a circular motion. Force components. Force components in a circular motion. Force components in a circular motion. Force components in a circular motion. Right. Again, look at the board. Again, look at the board. I'm going to consider an object again which undergoes in a circular motion. Okay, let's consider the object here, right? And say it undergoes in a circular motion with omega, right? There are two force components acting in a circular motion. Look at here. Look at here. The other most important thing. There are two force components acting in a circular motion, right? Namely, centripetal force and centrifugal force. Centripetal force and centrifugal force. Centripetal force is always acting towards the center, centripetal, and it's actually broken down from centripetal accelerations. Centripetal acceleration was towards the center. If there is an acceleration, there should be a force, and the vice versa is also there. If there is a force, there should be an acceleration because F equals ma, right? F equals ma. So this is centripetal acceleration and centripetal force, and this is centrifugal force, and this is centrifugal force, and this is centrifugal force. Centrifugal force. Centripetal and centrifugal, right? So two force components are there. The idea is such that centripetal forces are the forces which are acting towards the center, and centrifugal forces are the forces which are acting away from the center. Direction is away from the center. Centripetal and centrifugal, right? And since there are two force components, to travel this object in a proper circle, listen, to travel this object in a proper circle, these two components should be equal. These two components should be equal, because if centrifugal is greater, it leaves the circle in this kind of direction, because this drags to the right direction, right? If this force is greater, this leaves the circle in this kind of a direction. When both are balanced, it travels in the exact circle. Therefore, condition to be satisfied to travel in a circular motion is a proposed circular motion is centrifugal force and centripetal force should exactly be equal in a circular motion. Right? Okay. Take this down and copy down the diagram. Copy down the diagram and mark forces, mark all forces. And label these forces as well. Label this as centripetal force. I'll label it here. Centripetal force, and this is centrifugal force. Centripetal force and centrifugal force. Right? Finished? No. Take it down quickly. Take it down. Take it down quickly. Okay. Right. Now below the diagram, write down. Below the diagram, write down. To travel in a proper circular motion. To travel in a proper circular motion. To travel in a proper circular motion. To travel in proper circular motion, right? The requirement is these two forces has to be equal. Write down in red. Write down in red. Centripetal force equals this one. Centripetal force equals centrifugal force. Centripetal force equals centrifugal force. Centripetal force equals centrifugal force. Right? And highlight this. And highlight this. Highlight this. And next point, centrifugal force acts away from center. Centrifugal force acts away from center. Centrifugal force acts away from center. Centrifugal force acts away from center, while centripetal force acts towards the center, while centripetal force acts towards the center. Right? Then write down centrifugal force. Centrifugal force. Centrifugal force can be written as mv squared over r or mr omega squared. Same conversion. If you use r omega for v, you will get this. Same conversion. Right? Same conversion. Then write down this centrifugal force equals mv squared over r equals mr omega squared. So if the two forces are equal, won't they cancel each other as they act opposite to each other? Yes, they do cancel each other. They do cancel each other. And having that zero resultant is the requirement to undergoing the circular motion. Having that zero resultant is the requirement to undergoing the circular motion. Right? Centrifugal force equals mv squared over r equals mr omega squared. Introduce terms. Introduce terms. Simple m, mass of object. Simple m, mass of object. Right, start from here. Start from here. Since start from here and prove this. FC equals MAC. C equals MAC. Right? And highlight this. FC equals MAC. Right? And introduce terms here, these two terms here. Mass is introduced before. FC, centripetal force. Introduce the terms here. FC, centripetal force. FC, centripetal force. And AC, centripetal acceleration. And AC, centripetal acceleration. And explain that part, you are not audible. So what I was telling was centrifugal force is this, right? And then since we know centripetal force equals centrifugal force, no? Right? So this is the equation. Centripetal force Fc equals centrifugal force Fcf, right? Centrifugal force. Then I substituted these two for centrifugal force. I did v squared over r rho and r omega squared. Substituted. But in our acceleration components, we discussed that centripetal acceleration is v squared over r or r omega square, right? So therefore, from this, I replace this v squared over r with AC. Then we can obtain Fc equals MAC. Fc equals MAC, right? That's it. And introduce the terms as Fc centripetal force, AC centripetal acceleration. Centripetal force and centripetal acceleration. Centripetal force and centripetal acceleration. Centripetal force and centripetal acceleration. Right? Okay. Then below that, mention this point in red. Mention this point in red with an asterisk mark. With an asterisk mark. Therefore, this idea is very important. When you are writing also, realize it and write, and then I'll explain again. Write down. Therefore, when F equals MA is applied, therefore, when F equals MA, therefore, when F equals MA is applied, therefore, when F equals MA applied to circular motion, therefore, when F equals MA is applied to circular motion, put a comma, centrifugal force is automatically represented. Centrifugal force is automatically represented. Centrifugal force is automatically represented. Centrifugal force is automatically represented by product MA. Simple MA. Right? See, the idea is this. Now, if we use, look at here, if we use F equals MA for a circular motion, towards the center direction means centripetal direction. Towards the center means centripetal direction. So if we apply F equals MA towards the center, then F represents the centripetal force. And product MA automatically represents centrifugal force. Therefore, we don't mark centrifugal force in any circular motion. We don't mark centrifugal force in any circular motion because when we apply F equals MA, it comes here automatically. Now, if we mark it, we have to duplicate that force because it is automatically here. No? Understood? So this is the most important idea about the circular motion when it comes to applications. So therefore, we are going to solve applications using F equals ma without marking centrifugal force because it is represented by product ma automatically. Clear enough? Clear enough? Right? Okay. Next point. Next point. Keep using red. Keep using red. Red. Therefore, centrifugal force. Therefore, centrifugal force. Therefore, centrifugal force is not marked. Therefore, centrifugal force is not marked. Not marked. M-A-R-K-E-D, marked. Therefore, centrifugal force is not marked in circular motion when solving questions. Therefore, centrifugal force is not marked in circular motion when solving questions. When solving questions. Since it's represented by product MA in F equals MA. Since it's represented by product MA in F equals MA. Since it's represented by product MA in F equals MA. Since it's represented by product MA in F equals MA. Clear? Right? I'll explain this once again. Can you, yeah, you're asking also. Right. Once again, if I explain this, now when we are going to solve, listen again. When we are going to solve circular motion questions, what we will be doing is we will be applying F equals ma towards center. We will be applying F equals ma towards center. Right? In combined maths also, we will be doing the same. In physics also, we are doing the same. And anywhere, we will be doing the same for circular motion. Right? We are using F equals ma towards the center. Then, when we use F equals ma towards the center, this F represents centripetal force, no? Because these are the forces acting towards the center. It represents centripetal force. And product MA equals MA, no? Product MA. But this A is centripetal acceleration. But if I expand centripetal acceleration like this, again it ends up having the product of this, and that is centrifugal force. That is centrifugal force. Therefore, we are applying F equals ma means what we have done here, in other words, is this is equating centripetal force to centrifugal force. Because product MA represents centrifugal force. Product MA represents centrifugal force. So therefore, applying F equals ma towards the center means automatically we are considering centrifugal force as well. And we are considering the equation between centripetal force and centrifugal force. Therefore, we don't mark centrifugal force again. Because it's there. It's already here. It is already included. Right? Therefore, we don't mark centrifugal force again. Clear? Can you repeat the second point? Second point? Second point? Therefore, centrifugal force is not marked in circular motion when solving questions. When solving questions, since it's represented by product MA in F equals MA. Since it's represented by product MA in F equals MA. Right? Right? Okay. Any questions up to this point? 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 All good. All good. Online? Online? Clear. Online students. What about new students who are there for the seminar? As I mean, for the first day, is it clear for you, new students, newcomers for the seminar? Clear. Yeah. Good. Okay then. Good. Right. Now, from here, actually, all theories of circular motion is done. All theories are done. Now, let's see how these theories are going to be used in our circular motion types. Now, initially, I told you that we have two motion types, vertical circle and horizontal circle. Right? Okay, as the next heading, write down circular motion types. Next heading, circular motion types. Circular motion types. Circular motion types. Circular motion types. Number one, horizontal circular motion. Number one, horizontal circular motion. Number one, horizontal circular motion. Horizontal circular motion. Right? And below that, write down when solving questions, horizontal circular motion, and below that, write down when solving questions, when solving questions, put a comma and row number one. When solving questions, put a comma and row number one. Write down. Consider vertical equilibrium. Consider vertical equilibrium. Here. Consider vertical equilibrium. Consider vertical equilibrium. So let's see how it's going to be used with the questions. The logic is this: if the object travels in a horizontal circle, it is not having any vertical movement. So therefore, it is vertical equilibrium. Vertical equilibrium. No vertical motion. No vertical movement if there is a horizontal circle. That's the argument. Right? And the second one, row number two, write down, apply F equals MA towards center. 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 Right? Number two, this one, main number two, vertical circular motion. Vertical circular motion. Vertical circular motion. Again, below that, when solving questions, put a comma. When solving questions, put a comma. Again, row number one. Apply conservation of energy. I'll explain the logic again for the vertical motion. Now, if there is vertically moving, the potential energy and kinetic energy changes. No? So, therefore, we are using conservation of energy. Now, in a horizontal circle, no point of using conservation of energy because potential energy remains same. That's a same horizontal movement. Here, first one, apply conservation of energy for vertical circular motion. Apply conservation of energy. And second, number two, same, apply F equals ma towards center. Number two is same as before. Apply F equals ma towards center. Apply F equals ma towards center. Apply F equals ma towards center. Fine. Okay. Now again use a red pen and with an asterisk mark, write down for any kind of a circular motion. Red. For any kind of a circular motion. 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 F equals ma is applied. F equals ma is applied for any kind of a circular motion. F equals ma is applied towards center. F equals ma is applied towards center. F equals ma is applied towards center. Right? Okay. So that's it as all theories for circular motion. Right? Now we are going to start applications. Right? We are going to start applications. First we will be starting horizontal circles. Right? So any question before moving into application? Any question, Nelly? Anything to clarify from circular motion? No? No? All good? Online students? Yes. In vertical circular motion, that is not vertically in equilibrium. Why? That's a vertical motion. Then vertically, that is not in equilibrium. Horizontally, will be no point because now there is a vertical circle like this now in a vertical plane. Then horizontally that is in equilibrium. But naturally, there won't be any forces acting horizontally. Therefore, no point of considering it. We will be getting 0 equals 0. Right? So listen. Now, if you think like now, if horizontal circular motion, if vertical equilibrium can be considered, if you are thinking like why can't we consider horizontal equilibrium in a vertical motion? The reason is this: vertical motion is something like this. It undergoes in a vertical plane, right? Then naturally there are no forces horizontally. It is actually in a vertical equilibrium. That is true. That is actually in a horizontal equilibrium. That is true. That is actually in a horizontal equilibrium. But there are no forces horizontally. Then no point of considering it because we will be getting 0 equals 0. That's why instead we are considering energy. Right? No questions. Right. As a heading, write down applications of horizontal circular motion. Applications of horizontal circular motion. Applications of horizontal circular motion. Go to page number 4 of tube. Go to page number 4, question number 1. Go to page number 4, question number 1. Go to page number 4, question number 1. Circular motion questions are very easy if you are thorough with, if you are solid with the knowledge here, the foundation here. Questions are nothing. You can play around with the questions. Right? Okay, go to question 1. An object of mass simple m travels in a conical pendulum. I will tell you what a conical pendulum is. Read out the question. Conical pendulum, mass its angle with the vertical equals theta. If the radius of circle is r, determine the angular velocity of object at this point. Right. Conical pendulum means, you know what a cone is, right? Cones you know. Ice cones. Right? Conical pendulum means something like this. You know the pendulum, right? Simple pendulum. You know. In all levels, you have simple pendulum. Look at here. Let's say you can see this, right? You can see this, right? Let's say this is a string. This is a string, and a particle is attached here. A particle is attached here like this, right? Now, if I give a displacement like this, it undergoes this kind of a motion, no? Something like this, right? This is called a pendulum. A pendulum motion. This is called a pendulum motion. Pendulum motion. And this is actually a part of a circle, part of a vertical circular motion. See? Pendulum motion is also a part of a circular motion. This is called pendulum, right? And for the same setup, if I rotate this horizontally like this, can you see what happens? If I rotate this or rotate it horizontally, see, this particle travels in the horizontal. Particle travels in the horizontal circle, and the shape creates here is a cone. The covered shape is a cone. With this point, the covering shape is a cone because this undergoes in a this undergoes in a horizontal circle like this. Can you see? It's a cone. That is called conical pendulum. So there are two types of pendulums. This is the normal pendulum, this motion. This is a normal pendulum. And if it makes a cone like this, that's called a conical pendulum. Right? Okay, that's a conical pendulum. That's a conical pendulum. That's the conical pendulum. Right. The question is, okay, now the string is attached to some point like this, and this is the string, and this is the object, right? And this is the vertical line, right? Now, conical pendulum undergoes like this, I showed you, like this, and the circle is vertical or horizontal. Circle is horizontal. Circle is horizontal. Circle is horizontal. And this is how the cone is made. This is the horizontal circle. The object travels around the base of the cone. Conical pendulum, right? And the other given data, this is M. And angle with vertical equals theta. That is here. Angle with vertical equals theta. And radius of circle. Now, if this is the circle, horizontal circle of this object, then center of this circle should be somewhere here, right? Now, in circular motion, it's a key thing to find out where the center of the circle is, because we'll be applying F equals ma to where? Towards the center. We'll be applying F equals ma towards the center, right? We'll be applying F equals ma towards the center. So therefore, we have to know where the center is. Otherwise, towards the center direction changes, right? So if this is the horizontal circle, it should be the center. Then if I need radius, if I mark these 2 points like this will be the radius of circle. Is that clear? So these are the things we can mark. Copy it down quickly. What they ask is determine the angular velocity of the object at this point, omega. Question is about omega. This is what we need to determine. Okay, let's see. Mark this, and I'll give you another small task. Complete the diagram by marking all forces here. All forces in the sense, now don't mark centripetal forces and centrifugal forces separately. Mark forces like mg, reactions, if there are tensions, tension forces, mark all forces. And some forces from them will act as centripetal force. Right? That is how it works. So mark our forces. Mark them. Sorry. Mark all forces. Finished? Right. Let's see. Let's see. Forces. What are the forces to be marked? What are the forces to be marked? Weight acting from here. Mg, what else? Tension is a string. So tension of the string like this. Tension. What else? Reaction. Yeah. Yeah. To exert a reaction, there should be a contact. Is there any contact with the surface here? No, no reactions. No normal reactions. No normal reactions because no contacts. No contacts. What else? We don't mark FC and FCF because that will be automatically coming. These forces are going to represent centripetal force and centrifugal force. Don't worry about it. Right? Because centripetal and centrifugal forces will be with the contribution of the forces acting here. Right? We don't mark them as centripetal and centrifugal forces. Right? So that's all. That's all forces we have. That's all. Right? That's all. Right. Now, since this is an inclined force, I'll extend this vertically. If this is theta, this is also theta. No? What are them? Positive angles. Positive angles. Right? Complete the diagram. Complete the diagram. Complete the diagram. Right? Okay. Now, answer these questions. Is this a horizontal circle or a vertical circle? Horizontal circle or a vertical circle? Online students? Is this a horizontal circle or a vertical circle? Horizontal. Horizontal. Then, to solve horizontal circle, what are the two things we do? To solve horizontal circle, what are the two things we do? What are two things we have to do? Considering vertical equilibrium and F equals ma to center. That's it. Which means by doing these two, we can solve any circular motion question. Very simple as that. Right? Now I'm going to consider vertical equilibrium. Right? So let's consider vertical equilibrium of this. Write down by considering, write down by considering, by considering, by considering vertical equilibrium of simple m. By considering vertical equilibrium of simple m. Vertical. Vertical means vertical. What are the vertical forces acting in this system? Tell me. What are the vertical forces acting on this system? Mg. Correct. What else? T cos theta. Right? Mg and T cos theta. Mg and T cos theta. M sin theta. Vertical equilibrium should be. Because Mg is already vertical. Right? Mg is already vertical. So don't dissolve M because then you will lose the vertical force. And Mg is already vertical, that is vertical downward. From this T, one component comes. Right? From this T, one component comes. Let me write down that component here. and this component comes as t sine theta, t cos theta, sorry. This component comes as t cos theta towards the angle, right? This component comes as t cos theta, while the other component comes here as t sine theta. So this is what happens if you dissolve it. This is what happens if you dissolve it. Right? Here, vertical equilibrium. Vertical equilibrium means vertical upward forces equals vertical downward forces. Vertical upwards I have t cos theta only. Vertical downwards mg. Right? We have one equation. I'll consider this equation as equation 1. Is it clear how I obtain this equation? Is it clear how I obtain the equation? Clear? Vertical equilibrium. Right? Take it down. Take it down. Done. Then, if vertical equilibrium is considered, then what's the next thing we have to do? F equals ma towards center. Write down. Write down. By using this argument should be written by using F equals ma towards center. In words, we have to write this because towards center is the direction. We can't show this direction by an arrow because when this rotates, towards center changes. Towards center direction changes. Therefore, we have to mention it by using F equals ma towards center. By using F equals ma towards center. F equals ma. Now I'll put the draw the arrow to satisfy the diagram. Towards center of this diagram is this direction, no? Right? And don't forget to write this in words as towards center. Don't forget to write this in words as towards center. It's a must. Right? Okay. Now tell me the substitution here. What are the forces acting towards center? Now I'm applying F equals ma towards center. Now this is the direction here. Towards center. Towards center. Understood? What are the forces acting towards center? T sine theta. What else? Online influence? mg? Online influence? What are the forces acting towards center? Now, you know, in F equals ma, F is the algebraic summation of all forces acting along that particular direction. Vectors, no. If there are inclined forces, we have to take the components. If there are perpendicular forces, they will be neglected. And towards the center, considered direction will be plus, and opposite direction will be minus. Right? Only force here is T sine theta. Because mg is perpendicular. mg is perpendicular. It will be neglected. So T sine theta only equals ma. Now this a is not another mere a. This a is actually centripetal acceleration. This a is actually centripetal acceleration. Centripetal acceleration can be expanded in two ways as v squared over rho omega squared. Centripetal acceleration can be expanded in two ways as v squared over rho omega squared. Now, what is our final target? Omega. Our final target is omega. So then don't expand as v squared over r because we don't need v. Expand it as r omega squared. Right? R is given. Then this is r omega squared. Simplify this. Simplify this. So before simplifying, let me consider this as T sine theta equals mr omega squared, equation 2. Equation 2. Equation 2. Okay. Now listen. I don't need T. I need omega only. Right? So what's the best option here onwards to simplify this two? Substitute. Subject omega. Then T. T is not given. T is something put by us. We have two equations and two unknown variables T and omega. I need omega only. then T should be removed. T should be cancelled. So what's the proceedings here onwards? What's the easiest way to proceed here onwards? To cancel T. What's the easiest way to proceed here onwards to cancel T? Divide. Divide. Division. Divide the equations, and when you are dividing also, tell me, uh, is it is you divide 1 by 2 or 2 by 1? Here, if you divide this way, cos theta over sin theta create. If you divide the other way, sin theta over cos theta comes. What's the best way? 2 by 1, because sin theta over cos theta over sin theta, sorry, sin theta over cos theta can be written as tan theta, right? 2 over 1, and simplify. Simplify. Very simple. Finished. Right. Okay, 2 by 1. I'll be doing the simplification here. So at the board, if you didn't do the simplification, if you have already done, check your answers. 2 over 1. 2 over 1. I'll be doing here. 2 over 1. 2 is t sin theta, and 1 is t cos theta. And mr omega squared over mg. Right? T to T cancels, M to M cancels. Sin theta over cos theta is tan theta. Sin theta over cos theta is tan theta. Right? R omega squared over G, subject omega, we asked to omega, G tan theta, G tan theta over R, whole thing squared. G tan theta over R, whole thing squared. Okay, got it? Okay, G tan theta over R, whole thing squared. Sorry, whole thing root, not the square, whole thing square root. Okay. Online students, is it clear? Two by one, yeah, 2 by 1. Otherwise, you will get 1 over 10, right? You will get 1 over 10 if you divide the other way. Again, you have to cross multiply, no? That's why I divide 2 by 1 at once. You can divide 1 by 2, then cos over sin is 1 over 10, not 10. Right? Clear? Good. Others? All of you clear about the application? There's nothing here actually, if you have understood. And from the conical pendulum, these are very popularly coming type of questions in circular motion is a conical pendulum. Now, if you know conical pendulum, questions are nothing. And entire circular motion is like that. Circular motion is not a difficult part. Right? To be frank, circular motion is not a difficult part. Right? Compared to rotational motion, circular motion is easy. Right? Less theories. Now, theories are done now. Right? Less theories. Less theories means always it's simpler. Right? Any questions? All good. Right? All good? Okay then. So I'll let you do question 2 in tute as a homework. Mark question 2 in tute as a homework. Try 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 question 2 as a homework. Q2. Question 2 in tute as a homework. Okay. Any other questions about anything? Any other questions regarding anything, about anything? No? Okay. Right. So then, here I'm going to wind up the class. Now, our next day plan is this. Listen. Our next day plan is this. Now, all theories of circular motion is now being done and first application is also discussed. Right. Therefore, our next day plan is we will be spending the entire day with applications of circular motion. Right. We will be spending the entire day with applications of circular motion and especially applications of horizontal circular motion. Right? And we didn't touch the vertical circle yet. We didn't touch the vertical circle yet. Still behind the horizontal circle now. Right? First, I'll complete all horizontal circle application types, and then I'm going to go to vertical circular motion application types. Right? So therefore, next day plan is we'll be spending the entire day with horizontal circular motion application types of horizontal circular motion application. Right? So this is just the start of circular motion, just the start, and I started with a simple question. As usual, we are starting with simple questions and moving towards the advanced questions. No? So next day we will be moving here onwards towards the advanced question sites, towards the advanced question. Right? Okay, so don't miss the next class because we will be finishing horizontal circular motion on the next day, completing all the advanced questions as well. Right? Okay, so that's the plan, and then we'll be moving to vertical circle. Right? Okay then, and next sport exam will be coming up. Right? From what? What was the last sport exam you read? You have read? Fiction. Okay then. You didn't write rotational motion or no? Yeah, we finished the last today, no? Right. So next sport exam coming up is rotational motion. Right? It will cover rotational motion like torque equals I alpha applications, F equals ma, torque equals I alpha, and angular momentum. Those are the parts it will cover. So go through and get ready yourself for that sport exam as well. Rotational motion sport exam is also coming up within this month, in coming weeks, maybe next week. Right? Somehow during the month. Right? Okay. So that's everything by my side, and we'll be discussing all other questions in the next day. So I'm going to wrap up since there are no any questions. Right? Okay. So don't miss the next class because we'll be doing all applications on the next day, all other applications on the next day. Right? And try the second one and come to the class. I'll discuss the class before going to the other applications. Right? Okay then. Then I'll be winding up the class here. Right. Good night and goodbye. See you all in the next class. Stay safe and go safe. Today, the May Day, no? May rallies and all those things are there, and I saw some buses are going here and there in the afternoon as well. In the noon and afternoon, there were buses with flags and all that. They were like chill guys. They were going in the bus, right? So be careful when you are going. Right. Goodbye.